Hello and welcome to another power electronics class. In the previous class, we finished the DC to DC converters. We will get back to that in future classes to solve for the harmonics and so on. Today's class, we will start the AC to DC converters, which we also call the rectifier signal system as well, circuit as well. So what is a rectifier? A rectifier converts AC signal to DC or pulsating DC voltage. And then we add a filter to eliminate the AC components, which are the ripples of that pulsating DC. To create a constant DC voltage. We want the voltage to be very close to what the same voltage that we get from a battery. So final goal is to go from AC, and that could be any type of AC. We can have a sinusoid, we can have a triangle, any type of AC to a perfect DC signal. Rectifiers are the most, I could say, widely used power electronics. You would see it virtually in anything around you, from computers, laptops, your TV, all the electronics that you see in your home, they have to convert AC to DC. So all the electronic devices in your homes, even your fridge, or your washer dryer, you may think, oh, this is has an AC motor, but all of those right now are basically computers, have computers in them. Your washer dryer, you want to put it on different programs, settings, timers, temperatures, all of that has an electronic component. So it has an electric component, which is the motor, for example, for a washer dryer. And also you have all the controllers, which are electronic based. Same thing for your fridge as well. Nowadays, these fridges, some of them also connect to your phone as well to see, for example, if you left the door open in your fridge. So all of that has IoT, different computers to optimize the performance of and actually reduce the power consumption of a fridge. All of that electronics, and those electronics need DC to run. Therefore, it must convert AC 120 volts, 60 hertz to DC to be able to operate those electronic devices. So a basic rectifier converts AC voltage to a pulsating DC. This graph shows an example of an AC to DC rectifier. First step, and for those who had electronics with me, this was part of actually your final project. For those who didn't have electric devices and circuits or electronics with me, we have several stages. The first stage is a transformer, because we need to decrease the voltage from 120 volts to the desired voltage, which could be 12 volts or 5 volts. So the first step is a step down transformer. So for example, here, if N is 1 to 10, then the output voltage would be 12 volts. So we're going to have a voltage that initially looks like this, very, very high amplitude. Then, for example, 120 volts. Then we will convert it to another AC signal, which has the amplitude of 12 volts, for example. Then we use a diode rectifier. The most widely used is the bridge rectifier to go from the AC to the pulsating, I could say, DC thing. So we eliminate the negative part, and we have all positive, pulsating signal. So doesn't look like DC at all. Next step, we add an RC filter. And the RC filter builds a pulsating DC. Do you remember how we did this? We use a storage element, like a capacitor that charges and then slowly discharges. So you're going to have these peaks, and it actually looks like that, So what the capacitor does actually charges and discharges and creates this pulsating DC, which I show with red. And finally, we can add a voltage regulator in our, for example, we can use a 7805, which is a positive 5 volt, and we use 7805, for example, in our project in electronics. And finally, we have the load, which could be a phone charger, so you can charge a battery with it or turn on an LED. In the electronics, we had a potentiometer pot, which controlled an LED, if you remember, and you could dim the LED. Now we have different type of rectifiers. The simplest type of rectifier is made out of only one diode, and we call it a half-wave rectifier. And half-wave rectifier, we also use it, but not that often. And one example for this would be hair dryers. Usually the hair dryers have different speeds. They have low, high. And what we can do is we can run, so for example, if I connect this part, it's going to be the high. If I connect the second part, it's going to be the low. And what a half-wave rectifier does is, as its name states, it cuts the lower half of the signal, and you're going to be left with only the positive side. Obviously, we have a diode. You can only pass the current in one direction. You can't pass the current in the opposite direction. It doesn't go that way. Therefore, you're going to be left with half of the signal. And when you put it on low, it will connect the other side of the diode or the output of the diode, and therefore you can have a half of the energy delivered to the system. And the speed and the temperature drops when you have half of it. In real world, half-wave rectifier, the efficiency is around 33, 34%. It's actually less than half because you have waste in the diode as well. Obviously, the diode, you have a forward voltage drop in the diode, and it's around 0.7 volts. And by the way, and that creates heat and waste in the system as well. So you're not going to have like 50% of the power. It's closer to 34, 40%. It's not like it's going to exactly cut. And the reason, a couple reasons. Number one, for the diode to be in forward bias, you need a 0.7 volt voltage. So the diode will not even turn on it until the voltage is 0.7 volts. And when it turns on, there's a difference between the input voltage and the output voltage. And again, this is 0.7 volts. Why? Because the forward voltage bias of a silicon diode is 0.7 volts, meaning it needs 0.7 volts to turn on. And that is a drop that you see in the forward. And then it's going to cut again here at 0.7, and you're going to have again here turning on at 0.7. So you can see the difference between these two is wasted, and also you have all of that wasted, and this power down here is also wasted. So again, efficiency around 34%, I would say. Okay, and we showed efficiency. So the problem with half-wave rectifier, if you don't care about efficiency, hairdryer, obviously you're wasting a lot of power. 99% of the power is wasted as heat. You don't care about, another 40%. So, and you want to make it cheap, so you don't care. But if you want to build a charger, you don't want that to be wasted, or if you want to build a TV or I don't know, any type of electronic devices, obviously you don't want to waste power. First of all, the one main reason you don't want to waste energy. Second reason is that where does this wasted energy go? This wasted energy is heat, perfect, generates heat. And in a hair dryer, you have the fan, it's just going to run like a few minutes. It's not a big deal. But for a TV that runs a few hours, you need a huge heat sink, and you need a huge fan. No one wants to watch a TV and the fan noise going on at the back. So it's going to be very loud, uncomfortable. Obviously, waste 50-60% of the power would be wasted, more than 60% actually. And that's not a good solution. So therefore, better solution is called a full wave rectifier. And this is one type that we call a bridge rectifier actually. We have different type of full wave rectifiers, but the most commonly used is called the bridge rectifier. So a bridge rectifier is made out of 4 diodes. And in each half cycle, I could say, 2 of the diodes conduct the current. So 2 of them are blocking the current. So for scenario number 1, and we have 2. For scenario number 1, because this is positive, negative, again positive and negative, the current is passing through diode number 2 and then through the load and diode number 1. So D1 and D2. But because this is positive and negative, this one is closed. And again, because we have negative here and a little bit of positive here, this one is also closed. Again, this is connected to the negative. So these 2 are disconnected and D1 and D2 are working. And so this is for the positive cycle, and when we get to the negative cycle, what happens is now this becomes positive, this upper one is negative, and because this is positive, this is negative, this is going to conduct. Again, this is negative, this is positive, this is going to conduct, but since this is negative, this is going to be disconnected, and since here is negative, we have this one disconnected. Now the genius thing about this design is the way that the current is passing through the load. Can you tell me the direction of the current passing through the load in scenario number 1 and 2? Is it going from right to left or left to right? Through the R. So what is the direction? Right to left. So for both of them, the direction is right to left, meaning on the right you have a positive, negative, positive, negative. So no matter which cycle we are, always the current passing through the output is going to have the same polarity, meaning the positive and negative is going to remain the same. The direction of the current is remaining the same in the positive. So no matter which cycle we are in, the output is always going to be positive. So you can see Vs here shows our input voltage, and Vout shows our output voltage. And you can see that Vout is just constantly pulsating in the positive. Vn is going positive, negative, but Vout is just completely always positive. And there is a difference between the input and the output, and we show it with V lambda, and it's actually 2 V lambda. Why is it 2 V lambda? And this is, V lambda is actually the 0.7 volts that we have. Why is it 2 of them? 2 times 0.7, it's going to be 1.4. If it's a silicon diode, by the way. Why? Because previously in a half-wave rectifier, we would only pass 1 diode. Here we're passing 2 diodes. We're losing 0.7 volts here in forward voltage and 0.7 here. Okay? So we're using 2 times 0.7, which is 1.4 volts is reduced. So this voltage, if it's a silicon diode, it's going to be 1.4 volts. And to turn on this system as well, you need at least 1.4 volts of voltage. So the on point would also be 1.4 volts. And you can see that the frequency technically has doubled because you had one full cycle, which there it was T. Now this one is half of that. It goes one, so you technically double the frequency as well. You can see that this goes in half of that cycle to a full cycle of its signal. Now, obviously, this is a pulsating signal. We need a DC clean signal. If we give this to our system, it's just going to turn on, off at all time. It's going to damage our electronics. So what we need is we need a storage element to store the energy and keep that voltage at the peak. What we can do is we can add a capacitor, C, or RC, and what we actually do is we add an RLC, and that acts like a filter and reduces the pulsating system. So initially, the capacitor is empty, it starts to charge, and when it's fully charged, because this is a large capacitor, it takes time to discharge. And the moment that it discharges, and by the way, because this is our input and the output of the full pulsating is this black one that I'm drawing. And at the next cycle, it's fully charging and it's want to discharge, but you're going to charge it again at the next cycle and the next cycle and the next cycle, so on. And you get the bottom graph. You can see. So this is called the ripple effect. The ripple on the DC output is VR, and this is very important, Vm over 2 FRC, where F is equal to 1 over 2 TP. And TP actually is between these two peaks. You can see. Why is it 2 TP? Again, we have to get it from, our frequency is from here actually to here because this is our total, okay? And that between the peaks is going to be TP. So from here to here is TP, and from beginning to end it's going to be 2 TP. As I mentioned, the frequency is doubled as well. So it's equal to the frequency that we have, for example, of the sinusoid outlet, which is 60 hertz. So now, the proof for this comes from this equation. I wrote it down. VR is equal to Vm minus VL, and VL would be Vme power negative T RC over RC. And then we have the Taylor series expansion. We can use that. So finally, Vm would be T prime over RC. VR would be Vm T prime over RC. And T prime is equal to almost TP, which is TS over 2. Therefore, VR would be Vm TS 2RC over 2RC or Vm 2F RC. Now let's solve an example for it. We want to find VR for the problem, the figure you see, I'm going to call it figure 1. And for this, V peak is 10 volts, as you can see. The frequency is, let's say, 100 hertz. R is 10 kilo ohms. And C is 5 millifarad is, let's say, 500 microfarads. And we want to find VR. So this is part A. I want to solve it also for part B. Everything is the same. I just want to change C to 50 microfarads. So one, solve it for 500 and then solve it for 50 microfarads. What is the answer? Perfect. Perfect. 10 millivolts for A, and okay, C is 50 microfarads in the second one. Yeah. Oh, I'm sorry. Yes. So Vm is 10 over 2 times 100 times 10 times 10 to the power of 3, because it's in kilo ohms, times 500 times 10 to the power of negative 6. So this gives us 0.01 volts, or in other words, 10 millivolts. Am I correct? Yes. And for part B, it gives us 1 millivolts. It's 50 microfarad the second time. I'm sorry. 100, yes, thank you, 100 millivolts. Perfect, yes, 100 millivolts. So what does this show us? The larger the capacity, by the way, VR is the difference between VM and VL, which is our ripple. So the larger the capacitor is, this would be smaller. So first scenario, this is 10 millivolts. But when the capacitor is smaller, it means it's discharging very fast. And in the second scenario, this difference is 100 millivolts. So the bigger the capacitor is, it's going to have less ripple, smoother signal. The smaller the capacitor is, it's going to obviously. And same thing for the resistor as well. If you have a very, very large resistor, then it's going to drain the capacitor much faster, and then you're going to have a much bigger ripple. Now we can expand the same thing and create a three-phase bridge rectifier. Why do we need a three-phase bridge rectifier, you may ask? In some applications, for example, HVDC, high voltage DC, you want to convert it to DC and then transmit it 400 or 500 miles and then convert it back. In those cases, we need a three-phase. So a three-phase bridge rectifier utilizes 6 diodes, and we have 3 phases, obviously. And the output signal will look like this. We have 3 phases. Each phase has a 120-degree phase shift, but all of them have the exact same voltage. So peak to peak is the same. And they have the same frequency as well. So frequency is the same, voltage is the same, peak voltage is the same, but we have a 120 degrees phase shift. Now, because the distance between the peaks are smaller than a single phase, so a single phase, this was one peak, and you can follow this signal, and you can see the other peak. I'm just going to, and our other peak was here. So I had to bridge the gap between these two, which was enormous, okay? But at 3-phase, the peaks are pretty close, okay? So it's going to give us actually a smoother DC signal. It's going to give us something better when you convert it to DC. And it's going to be done to deliver much more power. So building a 3-phase DC is actually gives us a much better control and a better, smoother signal. Now for a 3-phase signal, to convert it to DC, first we use obviously the bridge rectifier, and you can see that here we have just the peaks connected, the peaks, and it doesn't even go to 0. You can see that it stops here and you have the pulsating DC. Without the capacitor, it looks very close to DC. And here we want to find the area under it to see the delivered voltage and the output voltage. So VD here, which is the output voltage, is going to be VAB, which is square root of 2 VLL cosine of omega t. And VD out is going to be 1 over pi over 3. And the area under it, integral of negative pi over 6 to pi 6. So we want to find just this area to be able to find the output voltage. So it gives us 3 over pi square root of 2 VLL, which is 1.35 VLL. This is important. So the average value of DC side voltage is going to be equal to 1.35 VLL. And what is VLL? VLL is the line-to-line voltage, or what we call just a line voltage. Now, for high voltage situations, we usually use a different device than diode. We use thyristors. So thyristors are thyristors, sometimes they call it, are devices that are used for high voltage, high power applications. And the graphics are like a diode with an extra pin input. So a diode has 1 input, 1 output, 2 terminals. A thyristor has 3. So it's like the diode, and we have an extra pin over here, which is technically a control pin. The diode, we have different type of diodes, like single and two-way diodes, and two-way, thyristors. And the single way, you just have single control. You just have control over when to turn it on, and you can't turn it off. It automatically turns off when you are in reverse bias. But turning on, you have to initiate it through the control signal. And this example shows a single-phase thyristor converter system. And the diagram is exactly what you had in a full-wave bridge rectifier, but we just replaced the diode with the thyristors. Again, this is for very high voltage applications like hundreds of thousands of volts or thousands of volts, you can use the thyristor. Now, a one-phase thyristor converter waveform looks like this. The good thing about thyristor, and sometimes it's good, it's a benefit, sometimes it's a disadvantage, is that we have control on when to initiate and start the thyristor. And on the bottom right, you can see a very nice graph of showing different times that we could trigger and turn on the thyristor. So the bottom one, the blue, shows the point that we turn on the thyristor, and therefore, and the upper one shows the output signal. Okay, so if I turn it on at this point, for example, if you can see, the signal will look like this. If I turn it on at the middle, then the signal will look like this. Now, what advantage does this give us is that this gives us control on how much power we want to deliver. Sometimes we don't want to convert 100% to the output. This acts like a switch as well. You can convert 50% of it or half of the signal. Okay. This is for an ideal one. Yes. Thank you for bringing that up. In real world, you have several volts under this for the output, and you have a delay as well. It doesn't trigger at the moment that you give it a control signal. So this is, yes, obviously for an ideal one. And on the upper side, you can see the pulse coming in, which is a control pulse. And at the lower one, you can see that we shifted the lower pulse a little bit. Therefore, the time that it starts is a little different than what we had on the top. So for this example, this is the pulse that controls the thyristor, and I'll explain more about the thyristors as well. And you can see that now our signal is starting from this point, and again going and starting from this point, and so on. Now, VD alpha for the thyristor is going to be 1 over pi, the integral from alpha to pi plus alpha, square root of 2 Vs sine of omega t d omega t, which is going to be equal to 2 square root of 2 over pi Vs cosine of phi, which is going to be 0.9 Vs cosine of phi. Now, let me give you an example of this. And by the way, VD alpha is the output voltage at the point that we trigger it. And we show that trigger point with alpha with the degree. So for example, here it's like 30 degree, in the middle is like 90 degrees, something like that. The point that of the signal, the phase of the signal that we start triggering it. Yes, do you have any questions? Yes, this is the degree that we start initiating. So obviously you can start from 0 degree, and then 90 to 100. 180 gives us again 0. Why? So what is cosine of 0 degree? Perfect. So if you started from 0 degree, you're going to have the whole signal. If you started from 90 degree, what do you have? 0. Yes. So there's a little bit of, this is 45 degree Alshi, and this is, when you have it at the end, it's 90 degree. Okay. Now let's solve a practice problem for this. We want to find the output voltage, or VD alpha, for alpha at 60 degrees and alpha at 30 degrees and alpha at 45 degrees. And our Vs is going to be equal to 10 volts. So Vs is 10 volts. We want to find V out at 30, 45, and 60 degrees. And this is the equation, 0.9 Vs cosine of alpha. Okay. So what is it at 30 degrees? It's going to be 0.9 times 10 times cosine of 30 degrees. And what is this? Thank you, 7.8. And what about 60 degrees? 4.5. And what about 45 degrees? 6.4. So you can see that at 30 degrees, it's at max. And then we have the middle, 6.4, and then 4.5 at 60 degrees. Okay. Is this clear, or do you want me to explain it? Clear? Yes? Okay. Can I go to the next slide? Okay. So thyristor, we have a control. Now, where is this beneficial? You may think we can use example for a voltage regulator at the end, or a voltage divider. But this actually acts like a switch as well and gives the benefit of switch. So you don't have the loss in the power as heat. So imagine you have 1,000 volts in the input and you just want 10 volt DC. And using this system, you don't even need the transformer. You can just switch it, and be able to extract and not waste that much power in the system. Okay, so it acts like a switch, and you could save power actually. But the downside is obviously you need a control system to control alpha exactly. Therefore, you need to add the control system control part, which could be an op-amp or a controller like Arduino or something like that. So you're adding additional parts, the control part, but you have control over the output. Now, for a three-phase thyristor, again, the combination is exactly like what you saw in a three-phase rectifier. You have 6 of these thyristors. There you had 6 diodes. And when you combine them, again, you're going to have the same thing. But again, this time, you have control on when to trigger or initiate or turn on the thyristor. And for a diode, you don't have control over that. As soon as the voltage reaches 0.7 volts, it turns on. For a thyristor, you can't control it. And the equation is going to be very much more complicated than the one phase. I just wanted you to learn about the waveform and how the waveform works actually. And again, you have an alpha, that's the degree that you initiate and trigger the thyristor. Now, the next thing is the characterization of the nonlinear loads. We have diode rectifiers, which are nonlinear loads, and we have which have nonlinear loads. We have to find the power factor, the displacement power factor, the total harmonic distortion, and we will learn about the harmonic guidelines of IEEE 519. Now, a power electronic interface usually looks like this. We have a converter and we have the controller. We have the source connected with the load with the converter. And the voltage link structure looks like the lower one. We have, if we have a DC to DC or AC to AC, we usually have utility connected to a rectifier or an AC to DC. And if we want to have an inverter system, we have another DC to AC system. But these systems create some problems, lagging or leading power factor, and I'll explain what we have here. Whenever you see a capacitor or an inductor in a AC system, it's going to create some problem. It's going to create leading or lagging power factor. And to learn that and the harmonics and the distortion that it causes, we need to, again, study the power factor. So this is just a reminder of what power factor was. We have linear and nonlinear loads. For linear loads, the power factor P, the signal is going to be P as V as Vm cosine of phi. The power P is going to be Vs Is cosine of phi. the power factor was P over VS IS, which is going to give us cosine of. In other words, it was real power to the apparent power, if you remember. And IS would be P over VS times power factor. Now, this is an illustration of what power factor looked like. Imagine we have this horse that's pulling a carriage, for example. If the horse is aligned with it, it's going to be perfect, meaning the real power and apparent power are aligned. The reactive power is 0. And that's the best case scenario. We always want the reactive power, Q, to be close to 0. And we want the real power to be equal to the reactive power. And if you remember again, this was our real power. This is reactive power. And this is apparent power, S. Now, the reactive power could be positive or it could be negative, leading or lagging. And when it was negative, we have a capacitive load, C. When it was positive, we had an inductive load, or L. And the power factor alpha or phi, or here we show it with theta. Cosine of theta is going to be our power factor, which cosine of theta, as you can see from this picture, is going to be equal to P over S. Now, the real power P is equal to V I cosine of theta. The reactive power Q is going to be VI sine of theta. The real power unit is watts. The real reactive power is volt amp reactive. For an inductive load, Q is greater than 0. For a capacitive load, Q is less than 0. What about a resistive load? For the resistive load, if we have a resistor, what is Q? 0. If you had measurement instrumentation, we solved it for average reactive power for a resistor. It's not storing any energy, so it's going to be 0. Q is 0. So, and a resistor, you only have real power. And the real power is equal to the apparent power. So resistor P is equal to S, actually, and Q is equal to 0. For apparent power, unit is volt amp. And that's the unit you see on transformers, all these power. You have kilovolt amp, which shows the reactive and the real power. And what is the relation between S and P and Q? S is equal to square root of P squared plus Q squared. And the unit again for Q is VAR, or sometimes we show it with kilovolt amp reactive. Now for a nonlinear load looks like this. It's a little different. For example, here we have VS, but IS in this system, because we have a nonlinear situation, it cuts at the middle. We have distortion. And this distortion is going to be equal to IS minus IS from the input. So the input current is looking like this, and you have this, the diode switching on and off, or the thyristor, and you're going to have a distortion which looks like this, it's not a DC, it's not an AC, and you don't know the frequency. It's very difficult to predict, and it's very difficult to model. And nonlinear systems create problem. One way to solve this is using Fourier transform. Obviously, as you know, Fourier transform is a great tool when you have a signal that you don't know the frequency components. And with the Fourier transform, you can find each of the frequency components of that and map it in the the frequency domain instead of the time domain. So we can obtain the harmonic components or the building blocks of the system using Fourier transform. This is just here for your knowledge. Obviously, you don't need to memorize any of these. So GT is going to be G0 plus sigma of H1 to infinite GHT. And when we solve it for the Fourier transform for H from 1 to infinite and phi AH and BH, we finally get to G is equal to G0 squared plus sigma of H1 to infinite G2 square of H. And here, tangent of alpha H is going to be negative BH over AH, and GH is going to be equal to square root of A H squared plus B H squared over square root of 2. Now, for a nonlinear load, the total harmonic distortion, THD, is going to be 100 times the distorted current, I distortion, over IS1, which is the source current. And we have the displacement power factor. So for a linear, we saw the power factor cosine of theta. We show it here with cosine of phi 1. The displacement power factor is going to be cosine of phi 1. So IS would be IS1 square plus I square of distortion. And P, which is the real power, is going to be VS IS1 cosine of phi 1, which is the displacement power factor. Therefore, the power factor would be IS1 over IS displacement power factor. In other words, the power factor is going to be the displacement power factor over square root of 1 plus the total harmonic distortion in the power of 2. And this is the proof for it. So the power factor as a function of the displacement power factor, P is going to be VS IS power factor, and we replace that with IS1 and distort the DPF, the distortion power factor, or the displacement power factor. And when we solve it, the PF would be the displacement power factor over IS over IS1. And we can replace IS over IS1 with this equation from our graph. And finally, we get the power factor over displacement power factor is going to be 1 over 1 plus THD, which is the total harmonic distortion. Now, the harmonic currents decrease the power factor, obviously. So you can see that the maximum of PF over DPF is going to be when we have the total harmonic distortion is at 0. And when you increase that, the power factor to the distorted power factor decreases. So the ratio of actual power factor to the displacement power factor decreases with the increasing total harmonic distortion. Now, these tables, we usually provide these tables when you have a system like this. This table is the IEEE 519, the total harmonic guidelines. And you can see that for ICS or I1 of less than 20, H less than 11, then you can see the different harmonics. And the most important harmonics that we have is the first, third, and fifth, actually. And the total harmonic distortion is going to be 5%, 8%, 15%, and 20%. As you can see, by increasing the total harmonic, you're going to decrease the power factor to the power factor displacement. And we measure this ICS with short circuiting or using the short circuit current. And you can see that there are limits on allowable harmonic current drawn by loads of various relative magnitudes. The relative magnitude of load current is based on short circuit ratio, or SCR. Again, this is just for you to know. So when we have a nonlinear load, it's going to create a distortion, harmonics, and it's going to affect our power factor. What is a nonlinear load? Usually when you connect it to a, capacitor bank, or, something like a inductor capacitor bank, it's going to cause nonlinear effect, and it's going to create distortion. And the higher that harmonics that we have, it's going to create more displacement power factor. And as we know, higher the power factor relates to the reactive power, and the higher the reactive power is, you're going to have more waste in the system. So summary of what we learned today: characterizing the nonlinear loads. We learned about that. The diode rectifier as nonlinear loads, the power factor, displacement power factor, and the total harmonic distortion. I'll explain more about total harmonic distortion in future lectures. And now let's have a small quiz. For a given power P drawn by a load at a given voltage, again, this is for attendance. You're going to get the full grade. Just want you to have your names. And I'm going to give bonus points for attendance. So question is, for a given power P drawn by a load at a given voltage level, the current drawn by the load is larger in magnitude if the power factor is smaller. True or false? Okay. Thank you so much. Perfect, yes. So the answer is, it's true. P is VI times the power factor, yes? So P is equal to VI cosine of phi or theta. Am I correct? Yes. So I would be equal to P over V cosine of phi. Therefore, if the current increases, then the power factor is smaller for a given voltage at a given power. So these two are fixed. When I increases, power factor decreases. So the answer is true. Thank you so much, and I will see you on Wednesday.